The engineering of pre-15th century Rus demanded precise geometry. The physical survival of structures like this white Orthodox cathedral proves an exact understanding of load distribution, spatial volume, and material stress. Beyond architecture, the civilization managed transcontinental trade routes connecting Scandinavia to Byzantium. Administrating this territory required a rigorous system of taxation, mass logistics, and standardized weight conversions across massive distances. Yet, if you look for the mathematical formulas that enabled these feats, you find zero theoretical treatises. The surviving textual record is empty. In contemporary Islamic or Byzantine cultures, historians can access extensive archives of algebraic proofs and Euclidean geometry. In Rus, there is nothing comparable. For decades, historians interpreted this lack of text as a sign of scientific backwardness. They assumed that because there were no written proofs, there was no complex math. In the late 19th century, V.V. Bobbinen began to challenge that assumption. Bobbinen argued that the absence of axiomatic Euclidean texts suggests a strictly utilitarian paradigm, a culture that valued the speed of final calculation over the preservation of the theoretical proof. To prove this, Bobbinen had to confront a literal void of data. The surviving record of pure mathematical theory from early Rus was effectively a blank page. He spent years searching archival collections for abstract formulas. He found no step-by-step arithmetic deductions, no written geometry. The mathematical operations of early Rus were predominantly oral and physical. When calculations were written down, they were etched onto highly perishable birch bark, meant to be discarded once a transaction was complete. To understand the logic sustaining this empire, Bobbinen looked past the missing blueprints and toward the primary constraint of their communication, the Cyrillic alphabet. The defining constraint of early Russian mathematics was its written numeral system, adapted from Greek alphabetic notation. Standard Cyrillic letters became numbers by adding a diacritic mark called a titlo. Higher magnitudes were built by stringing these letters together. Crucially, the system lacked a positional zero. Without positional magnitude, characters failed to align vertically, making written computation nearly impossible. Writing out a multi-step algebraic or arithmetic proof using this syntax was intensely inefficient. The characters themselves resisted computational manipulation on the page. This cumbersome written system forced active calculation off the page entirely. Computation became a physical and mental process, with writing used only to record the final static output. To bypass the limits of Cyrillic numerals, the culture relied on physical counting tools. The primary engine of medieval Russian computation was the shoti, a traditional abacus designed for rapid, tactile arithmetic. The shoti operates on a base 10 wire system, each rod representing an increasing power of 10. A unique 4-bead wire calculates fractions. By sliding beads left to add and carrying values to the next rod, the hardware handled the arithmetic logic in seconds. The kinetic speed of the shoti far outpaced the slow process of translating those changing values into written Cyrillic script. When the transaction was done, the merchant simply read the final arrangement of the beads and carved that single resulting number into a birch bark tally. The intermediate steps vanished the moment the beads were reset. In medieval Rus, mathematical certainty resided in the physical manipulation of the beads. The total absence of written proofs reflects a system where calculation was a performance rather than a record. There is one major historical exception to this textual silence, a manuscript written in 1136 by a monk named Kirik the Novgorodian. Kirik wrote a treatise on computus. This was the specialized ecclesiastical mathematics required to maintain a functional calendar. Kirik faced a high-stakes logistical problem, accurately predicting the date of Easter. This required reconciling the 354-day lunar cycle with the 365-day solar year over vast spans of time. When you read Kirik's methodology, you find that it operates entirely as an algorithmic checklist rather than an abstract exploration of time. To maintain exact accuracy, Kirik subdivided units of time into extraordinarily small parts. He took a single hour and split it into fifths, then 25ths, then 125ths, pushing fractions past the limits of physical measurement. Despite its conceptual complexity, Kirik's work served a strict administrative function. It was a logistical manual written so other church officials could successfully align their regional calendars. Even in this rare instance where a medieval Russian recorded complex mathematics, the focus remained exclusively on practical logistical outcomes. Evaluating these methods requires contrasting the Russian approach against the prevailing mathematical standards of Hellenistic and Western European cultures. The Hellenistic tradition prioritized abstract geometry, Euclidean proofs, and the pursuit of theoretical truths independently of their immediate physical application. The Russian paradigm was strictly utilitarian. It valued the speed of physical calculation, exact taxation outputs, and the administration of tangible resources. We can map this divergence clearly. While Arabic algebraic texts were flowing into Western Europe, early Rus imported Byzantine calendar math and pragmatic trade arithmetic, aligning with their specific needs. Optimizing for physical, practical output over written theory was a deliberate cultural adaptation to the demands of a vast, trade-reliant territory. Their system was highly advanced, but it was engineered for completely different parameters than the Euclidean models found elsewhere. This brings us back to V.V. Bobbinin. Bobbinin successfully proved that a complex mathematical reality can exist completely independently of formal written proofs. The heavy stone cathedrals and the transcontinental trade networks functioned seamlessly. The math was correct. It was simply calculated on the beads of the shoti rather than the pages of a manuscript. Bobbinin's research provided a framework for analyzing cultures that prioritize mental and physical algorithms over abstract theorems. To understand the technological capacity of a civilization, historians must look past the library and examine physical tools, study behavioral adaptations, and environmental pressures. A civilization's mathematical sophistication is demonstrated by the practical stability of the structures it builds and the networks it maintains.